Or they're gonna.
Fingers crossed.
Okay.
All right, are we recording?
Right. Can I give you an introduction
Sure.
very briefly? Usually I give you the formal introduction, but since we had some sort of time has passed quite a bit, so let's make a brief introduction. Welcome everyone. This is a fourth HLCS.
You had it.
Yeah, HLCS, the seminar series. Today, it's an honor to host Eric Dreger, who is a director of the HPCIC and the Radius project at Lawrence Livermore National Lab. And he is going to talk about Radius and the HPCIC outreach through the open source software. This is the first time doing the hybrid meeting. So let's see how it goes. All right. Yeah.
All right. Thank you very much, Jung-Soo. And thank you all for your patience while we figured out how to do this. As you can tell, we're learning as we go. So I'm Eric Dreger. As Jung-Soo said, I also want to call out David Beckingsale. He is the deputy of both Radius and the HPCIC. He is online right now. He's recovering from illness, but he's a trooper, so he's still here and he will answer questions in chat as they come up. He is the technical backbone, I would say, of both projects. So definitely I'm very pleased he was able to make it here. All right, so today I want to talk about sort of an old effort and a new effort and how we're bringing them together to try and do something impactful in terms of our external outreach. All right, so I'm going to start with sort of some context that I believe most people, if not all of them on the call, are not going to be unfamiliar with, which is after decades, I mean, those of us who've been doing this for a long time have looked back and realized we had several decades of relative stability on the computing hardware side, in that you could write a parallel code with MPI, maybe sprinkle in some OpenMP, and it would just run everywhere. And all you had really to do was maybe tune some kernels for the specific architecture to get the best performance. That is unfortunately not the case anymore. So this is a roadmap. This is all the DOE leadership class machines over the last 10 years. I've underlined GPUs where they show up, and you'll see some trends pop up pretty quickly. And so what we've in the very bottom row is the NNSA machines. That's the ones that Livermore, Los Alamos, and Sandia use. And then the top 2/3 is the Office of Science Labs, Berkeley, Oak Ridge, and Argonne. So as we have been computing and writing codes, there's basically 3 phases we've had to deal with. And the first was life was good. Like you had, GPUs were available if you wanted to try them out, but you could just ignore them, no problem. And we did. So we enjoyed that. Our legacy codes pretty much just worked. I mean, we did have some challenges. Blue Gene was not the easiest architecture to make run well, but it did work. So it was really more about how much performance you could get. However, at that, in about FY16 is when we realized we no longer got to do this anymore, because our biggest leadership class machine that we still have, Sierra, was going to be a GPU machine using NVIDIA GPUs. And on the open side, they had also gone full GPU. Summit was the open analog of Sierra over at Oak Ridge. And it just became clear that we couldn't ignore GPUs anymore. So there was a major shift, particularly at Livermore, on looking at all these large software bases that we had, these large multi-physics application codes, and realizing we had to get those able to run on GPUs, and rewriting them from scratch was not an option. They'd been written and validated over decades. And so we had to figure out a way to sort of refactor those in place and then put a strategy in place to develop new software going forward that could not just run on NVIDIA GPUs, but on pretty much any accelerator. And so that's the future we're looking at. Is we already are in the stage where if you run on the DOE leadership class machine next year, you'll have your choice of NVIDIA, well, not your choice, you'll be faced with either NVIDIA, AMD, or Intel GPUs. Each has a different programming model under the hood. They're very similar in hardware, but not exactly the same. So your performance is not going to be the same. So this is what we need to be ready for. And luckily, and by we, I mean all the people on this call who've done an enormous amount of work in the last 6 or 7 years, basically making this possible. And so what I'm going to be doing is talking about things that have come out of that effort that I was mostly a witness to, but really was very impressive and has actually positioned us, I think, somewhat uniquely to be ready to compute in the next decade in a way that I think others could really learn from. So this is sort of the premise of why we're doing outreach the way we're doing it right now. And that is that we now have this substantial portfolio of software, nearly all of which is open source. And this was a strategic decision around heterogeneous computing and HPC scientific computing that we believe really can be used in a broad class of applications and use cases, and that honestly we believe is one of our best tools for identifying commonality in the community and in the world and bringing people together. So this is what I'm going to talk about for the rest of this talk, is this portfolio that we have and how we'd like to use it to encourage outreach and collaboration. Because honestly, the problems we've faced and are continuing to face are problems everyone is facing right now. So this is the new HPCIC. Fred Streitz is on the phone. He is the founder of the original HPCIC about 11 years ago, I want to say. A fantastic initiative that really was designed to try and get out in the world and evangelize what we can do in HPC. And that is continuing, but the refocus is really around two major bullets, which I've shown here. One is focusing on our open source software portfolio. And so rather than trying to bring people into our walled garden and get them on our machines and get them, maybe we write their software very custom for their specific needs, we're trying to instead all work together on the same type, these same software packages, either to use them or ideally to co-develop them. And so, this benefits everybody. If we can all work on common areas of need and interest, we can move everything forward for everybody. A new area that we're really exploring is also cloud computing. So we don't anticipate replacing our big machines with cloud anytime soon, if ever. But what we are recognizing is that cloud HPC is becoming a real resource for a lot of people. You can prototype 5 different architectures very quickly, see how your code will run on it. But also it is now a mechanism that we can allow people to try out our software on the latest HPC hardware without having to get them accounts or have them buy that hardware. So it really is a much lower barrier to entry for people that we want to bring into the HPC world. And this is much more on the outreach side at the like grad student level. And then ultimately, as I said earlier, the goal is once we've got people engaged on these, they've tried out our stuff, they've realized this is a great solution for their problems, we now have a common point of entry to have really substantive discussions of how we can collaborate and work together further in the future. Okay, so that's the point of the HPCIC. That's our outreach arm. However, this whole strategy would not work as well if no one had been doing anything to get this software ready to be used in this fashion. But luckily, this is an effort that's been going for several years. David Beckinsale has been at the core of it. I really can't give him enough credit for the work he's done. And that is this Radius project. And Radius is an internal effort designed at going around the lab, identifying when these capabilities are being developed, and often the people writing them have written them with an ocean toward it being a common open source component. But ultimately, people are funded to write software for a specific project or for a specific program. And so what Radius has tried to do is help be a mechanism to take the software and make it stand off the rough edges, test it out in use cases that maybe weren't exercised in the mission area that it was developed for, and make something that's a little more generally usable for the community to use. It's also had a focus of going around the lab where we have applications that have not adopted this software, maybe because they didn't know about it, maybe because they didn't have the time or the expertise to implement it, and getting them, increasing our user pool, essentially, of trying to bring everyone up to the same level so that more applications around the lab are ready for this heterogeneous HPC. And then a third thrust of this project has been DevOps infrastructure. So we've started, it's become recognized that we can't expect the physicists and computer scientists working on these projects to do everything all the time. Like we need to start putting infrastructure in place for testing and build and the tools that you need to do modern software engineering for this complex HPC landscape, and do some of the groundwork to help make that easier, make that more powerful. And so this project has been working on that as well for the last couple of years. And so these two together, we believe, creates a very powerful combination of, we have a mechanism now to take software that is being developed for specific purposes, polish it up, make it more usable, and then move it out into the outreach side of things without having to have the people who developed it do all that work themselves. We're trying to take that off their shoulders as much as possible. So this is Radius. And this is basically kind of re-saying what I've already spoken to, but what I want to call out here is that things you may have imagined when I talked about open source software, often our brains go to one or two of these categories, but in fact, it's been a very broad effort. There's quite a lot of software that's being developed. And so I'm going to spend most of the talk walking through very specific software projects. And this is where it's a terrifying talk to give, because I think a lot of the authors are on the phone, so I'm going to almost certainly say things wrong on every slide. I'm going to mangle, I'm going to miss things that you need to say. But again, the point is, I want to expose people listening to this to the capabilities that are possible, because I think when you really start to dig in is when you see, okay, I thought I could handle time integration myself, but it turns out the way they're doing time integration has some features I had not even thought I needed, but I should be looking at. And so just as a commercial to get you to explore it more deeply. I'm going to speak to these 6 categories I've listed on the right. And please interrupt and stop if there's questions or clarifications you'd like, and particularly on the products, because I'm happy to then throw it to those on the phone to answer things more completely. All right, so we're going to start with build tools. Now this is where my background as a physicist, not a computer scientist, really comes into play, because when I think of build tools, I think of a make file that I dug out my dusty book and figured out how many spaces I needed so it would actually build. It turns out people are building codes a lot better than that now. So, which is great, because the way we used to build codes was the worst. So the first and probably one of our biggest exemplar open source projects is Spack. This is developed by Todd Gamblin and now is a massive open source project with contributions from around the world. And the premise is very straightforward, which is, how if you go to your Ubuntu system and you want to install software, you just you take a package manager and install a package, and there it is, and it works. Spack is basically that for HPC. It builds from source. It's not all binaries, although now there is a build cache where you can get some sort of pre-blessed binaries installed. But so much HPC software has such complex dependencies that just building all the libraries that you need to build your program has become kind of a heroic effort. And so what Spack does is it allows people to define that build process for each of the pieces, and then it cleverly works out the dependencies. You can specify compiler options and default compilers in such a way that you really can very flexibly build complex codes with a lot of dependencies in one go. And so this is something we think has really made life a lot easier for a lot of people, and is something that honestly all the rest of the projects following have for the most part adopted, and makes it much easier to try things out. Okay, see, it's very addictive. People hear about it and they try it, and then they're hooked. So I'm happy to hear that. Now BLT this is a perfect example of people over, like in our programmatic side, we have some fantastic computer scientists who are just trying to make their own lives easier. I mean, they're very altruistic, but ultimately they want to make their own lives easier. And BLT is, I think, a perfect example of, they had some great innovation and cleverness that, again, just to make their lives easier so they could build their codes better and have sort of some clever options sort of cooked into place, macros for, how you set up your CMake system, or how you build on a specific platform. And so as we realized what they were doing, and by we, I mean people at the lab, not necessarily Radius, we realized this is something that everyone could use. Like, just make CMake more usable and more powerful. And so this was sort of pulled out and pulled into an open source package, and honestly is something I think should be very broadly adopted, because if you infuse none of the functionality, the fact that when you go on a new architecture, someone has already sorted out all the CMake options for you, makes your life infinitely easier. You can sort of draft off the efforts of others and not have to reinvent things yourself. Shroud, this is basically, again, this gets back to my physics background, where when we tried to compile something that had Fortran and C in it, you just had to go in and do horrible plumbing and hook it up to create these interfaces. And in fact, it's really designed to simplify that process. If you want to call Fortran from C or C++ or vice versa, you want to go to Python and back. How do we set that up in sort of an easy and automated way? So this is a tool for that. And then when we think about GPUs, this is really, I was tempted to lead off with this because I feel like this is kind of our banner. This is what everyone wants. How do we run on GPUs? How do we manage heterogeneous memory? And so I'm sure you've heard of Raja. It, along with Cocos, is kind of the NSA's flagship open source software these days, which is, as we looked at these massive code bases, how do we take the work that's happening within those codes and run it on a GPU without having to rewrite the entire code and say CUDA. And this is what Sandia and Livermore people came up with, which is C++ has this notion of a lambda that allows you to pull a whole block of work and ship it off to a underlying back end. And so rather than trying to rewrite everything on the, every time for different architectures, can we define execution policies that just define how you run on an NVIDIA GPU and how do you run on an AMD GPU, and do that essentially throughout a code so that common work patterns can be abstracted and implemented once as opposed to over and over again. Now, this is a difference we have here from Cocos. Cocos is sort of an all-in-one memory manager, execution abstraction, task manager. We've done a little bit more separation here. And so Raja is our execution layer, Umpire is our memory management layer. And where the reason I like to call this out in this way is the fact that memory is sort of the trickier part of GPU programming that most people, when they first come at it, don't think about. They're thinking about how to rewrite their loops, in the appropriate programming model. But you forget that, often the performance gets hammered much worse by moving data back and forth too much or trying to do too many mallocs on the device. And so being smart about how you manage your memory and how when you can touch it, where it's going to be when you want to execute next is actually probably the more important thing for performance. And Umpire, this is actually David Beckinsale's, he is the lead on this. I believe he's developed most of it. Really is a powerful tool. And so memory pools is a big one. Being able to allocate in a smart way is a big one. And so, and not just for GPUs, but for even the multi-core systems with NUMA, you need to be able to touch memory in a way that's not going to kill your performance. Yes. No, these two are very complementary, and they were designed that way from the get-go. Most Raja codes at the lab use Umpire. You don't have to though. That's the nice thing.
Yeah, I think I was Raja, but
okay. And I'll highly recommend that you look into it. Yeah. Oh, thank you very much, Charity. So yes, so that was actually a comment or a question about whether Raja and Umpire work together, as well as whether they need to be used together. And you hopefully heard my answers. But yes, I will try to repeat the questions. Thank you very much, Charity. And then in the course of developing Raja, developing Umpire, the question came of moving data between spaces. Can we just design a layer that puts in some smart pointers and some tracking and some logic so that if I'm going to touch memory on the CPU or touch memory on the GPU, it'll initiate a move when it is not where it needs to be because it's kept track of where it was moved last. And so this is essentially a convenience layer. It's not required at all, but it's effectively a way to get managed memory in software, but not in a terribly unperformant way. So this is just an extra little fun layer that was added that I think is very clever. All right, and then this is LvArray, and it says containers, which I immediately was like, oh, that's odd. I didn't know we were doing containerization at this level, but this means more of a data structure, a software container in that respect. So complicated multidimensional arrays that how you access data, especially on the accelerators, is incredibly important for performance. And so this is a nice way to very powerfully question was, is it similar to Cocos and how they abstract the data structure? And I believe that's exactly right, that it's a much more flexible data structure you can map to the hardware. All right, and so CS infrastructure. So we have one of the sort of our main drivers of HPC at this lab is big multi-physics codes that do these very complex programmatic calculations. And so they are truly multi-physics. You have a lot of different standalone packages that are being called by each other, and they have to touch data. They may be on different meshing and totally different discretizations. And so ultimately, as they face this sort of revamp of how we're going to design code for the future in terms of accelerators, the computer scientists over there just took a long, hard look at how they did software development. And there's a report on the right that I have a snapshot of, which is honestly, I think it's going to be looked at by Livermore historians as a real turning point. It's going to be like our Magna Carta. I hope the authors online really liked that, because yeah, they're very modest people. Anyway, so the idea is, rather than each of these multi-physics codes designing all their own plumbing, doing all the I/O, doing all the viz, doing all the setup and input, and also how you have the codes themselves manage data as a package needs to compute some equation of state term and put it back into a place where the rest of the code can see it. They very thoughtfully sort of sat down and talked about how they can make common components for these activities that are not, don't have to be tied to a given code. So you can essentially hook things together now much more flexibly. And for the purposes of this talk, others could do the same thing. And so this is the AXOM project. It is, it's got quite a few pieces to it. I'm not going to get into the full depth of it, but the idea is you have very, very smart ways of managing data between these codes. So you have a key value in-memory data store. No worries. I think Siri wants to participate. Awesome. No worries. No, it's good. I like to have Siri weigh in when they can. A lot of tools around meshing and geometry management and viz and surface slicing, and it's all very impressive. I've seen sort of more in-depth talks on this, and there's a lot of machinery here that's incredibly powerful. So if this is something you think you could potentially take advantage of, I highly encourage you to look into it.
Not only think we'll take.
Excellent. Yep. So yeah. So and again, this is this is just sort of a list of the ways people can use the AXOM software, and it's not intended to just replicate a full multi-physics code. You can use it in pieces. You can use it in ways that were not originally designed, because it's been written generally enough that it can be reused in any number of ways. And then here's a list of some of the AXOM components. I'm not going to read through this. I'll provide these slides after for reference. But yeah, so this just to give you a sense of some of the cool things you can do. But just for example, CIDR is one that I was very impressed by, because you had Fortran codes and C++ codes on different meshes, putting information in a sort of central data repository and pulling it back out without having to make copies, without having to move data. It's performance-wise a fantastic solution.
Question on that.
Yeah.
So this in C++, C and Fortran, how does it practically accelerate?
So all this stuff has been designed. I mean, I don't know that every piece here will run on a GPU, but it's all designed for multi-physics codes to run on both AMD and NVIDIA GPUs. Yeah, where needed. Yeah, some of it may be up at the CPU and not ever get down to the GPU, but yes, no, it is all designed around the notion of a heterogeneous memory space. All right, now this is a more traditional open source that Livermore has been doing for quite a while, and this is the organization I'm in. CASC, the Center for Applied Scientific Computing, has been a leader in this area, is math and physics. And again, we in no way are the only people doing math and physics library development. These are long-standing efforts, but most of these libraries, if not all of them, are integrated with the rest of our software stack, such that to run on GPUs, the pieces I've mentioned before, these should integrate very nicely. And so one of the banner ones of these is MFEM. This is our high-order finite element library. This has been part of the Exascale Computing Project Seed Co-Design Center. It's been used in a number of applications. It's incredibly powerful, both from the math side as well as on the computer science side. Their GPU implementation is phenomenal. So I highly recommend you, if you're in any way interested in finite elements, to check that out. We have Hypre. This is one of the famous math products out of Livermore for multi-level solvers and preconditioners. Again, very GPU. They've done a lot of work on getting it on the GPUs, despite the fact that linear solvers on sparse linear solvers on the GPU is not an easy problem. And so they are at the forefront of that problem, but it is still an active area of research. This is a fascinating one, and I'm somewhat biased because this team is mostly in my line organization at Livermore. So I've gotten to know what they do maybe more intimately than some of the other projects. But again, this is where my physics training really comes out, because time integration, I had the classic physicist notion that it's like I can solve all that on my own. Like, it's a very straightforward idea. Delta T, I use that all the time. Like, no, it turns out time integration actually has some incredible sophistication, particularly for coupled algorithms. And so this project is a long-standing project. It just won a big SIAM award because it honestly has become incredibly impactful and just has such sophistication under the hood. So I've shown a few examples here on the right of some of the performance they can get, but they can get massive speedups just by solving the time element of the equations, you know, with a much greater awareness of the underlying problem and the time scales and the stiffnesses. So I highly encourage you to reach out and talk to those teams if you think they could help you. They're very friendly.
The
Please.
speed up there is by taking less time steps, is it? Being able to take larger?
So the speed up here, and I don't know if you can see it, but it's it's the fact that they can separate out the time scales and solve this. The stiffer piece has to be integrated more quickly, but the one that's not as stiff is expensive, and then they can ignore it for, you know, take bigger jumps through time on that side. I'm pretty sure everyone on that team is now irritated with me. that was a terrible explanation. All right, so LibROM, I'm proud to say, is part of the Radius portfolio. This is Young-Soo's project that he has been changing the world with. It's been growing by leaps and bounds. And I have to confess that when he started talking about reduced order modeling, I was very skeptical because this was a big topic a while back. But the problem was that, you know, from the physics side, there was concern that while it worked well in the areas that it was sort of trained, it was very hard to know how it was going to do as you moved away from that training domain, and particularly the fact there's sort of a lack of interpretability. So densities could be negative, or, you know, you get very unphysical behavior because it's just the math pushing and just trying to do its best, in an ill-defined problem space. And what Young-Soo has done incredibly well is brought physics constraints to the problem such that not only you have a lot more confidence in the predictions, and again, you might get to a regime where it's slightly off, but it's not going to be insane. But also, it really has increased the range of sort of extrapolation. So he's had some really fantastic early results that, you know, have massive speedups, but also when you recompare back to the full model are shockingly accurate. So it's incredibly promising, and I've seen you continue to apply it to more and more problem spaces. So I have become a believer, which again I was very skeptical. So that's hard to do. I think that's in his wheelhouse. Yeah, the question was about Lagrangian hydrodynamics, and I've already promised that Young-Soo can solve that perfectly. And then an area that has been an area of research for a while, but has become more and more important as we get to these massive systems with so much parallelism is parallel-in-time solutions. And the XBraid project it's a fascinating one because what they do is they're trying to speed things up by throwing additional resources to do this sort of solve of multiple time points all at once, kind of like an implicit solve. But then they recover the exact same solution. So it's a very well-defined and rigorous approach. It's not sort of let's just throw things out in the future and hope our guess was right. It's really a rigorous mathematical formalism, and it's one of these areas where you have nothing to lose. I mean, we're now in many problem spaces, we can't parallelize it anymore in the traditional ways. So why not throw some of those idle cores at it and see if you can get a speed up in the time dimension? And in fact, in many cases, the speed ups are significant.
In taking a resilience on the system's most.
I have no idea. You mean in terms of like fault tolerance of the machine?
Yeah, fault tolerance of the software. If you could deconstruct missing.
We should talk about fault tolerance because it's long been a position by many of us that it's a ghost story that has been told that has never come to pass and never will. So, yeah. No. So that has not been a major driver, I would say. Fault tolerance has not been something we've really worked too hard to respond to, and now that we're starting to see, it's not seeming to happen.
Okay. There would be, Eric, there would be benefits for fault tolerance because parallel-in-time, you are effectively keeping multiple copies of different fidelities of the solution around.
Right.
So you always have the ability to reconstruct. But that's not the primary goal. The primary goal is to make use of the excess parallelism you have, that when you run out of things you can do in parallel in space, to be able to actually accelerate in time since the processors aren't getting any faster.
Great. I've heard arguments along those lines before. I've just never seen a demonstration. So it's an interesting idea.
Yep. So that was Luke, and he was saying he that's what he's heard, but he has not seen a demonstration of it. And thank you, Jeff, for that clarification. That was much more well said than what I was.
So for instance, the Navier-Stokes examples that he doesn't have the speed up curves here, but that Navier-Stokes example Rob has shown, you can eventually you run out of parallelism in space because just strong scaling runs out at some point. But he can get significantly keep scaling that even further and make more use of parallelism by parallelizing in time. Then.
Right. Yep, that is the ultimate argument, and it's getting more and more compelling as we get these massively parallel accelerators with just ridiculous amounts of cores waiting to do work.
It's very exciting. If it's working and you're seeing some good results.
Yeah, no, it's very promising. So we encourage you to talk to that team further. All right. SAMRAI, I'm not going to get into this too much, in part because I've learned through my ECP role that adaptive mesh refinement is apparently a religion, not so much a math problem. So SAMRAI is our Livermore flavor of that. It's, as far as I can tell, very beautifully designed and powerful, but I won't try and make any comparisons because that's dangerous. And then this is something that honestly has become more and more critical as understanding performance has gotten more challenging, and then also managing the more complex workflows we are imagining as tools like AI and ML come to the forefront. So Caliper is our tool for instrumenting and measuring performance. It is a very straightforward thing, but it is, as they've sort of converged on this common format that all the codes are using, it has made sort of analysis tools significantly more powerful because you can trust that you can query any number of codes and get information out in a standard format. And so the Caliper team has really been sort of instrumental in some of our other performance tool efforts. But as a standalone product, it is also quite nice. It's the same thing we all have been doing ourselves, of putting in timers and printing them out and trying to analyze them, but it just sort of does it better and all at once. Now, this is a fascinating thing. This is Spot. So this is a database that we run on our machines that basically pulls that data from, generated by Caliper and puts it in a database. So you can actually track over time your performance of applications. You can see if things are degrading. You can do a direct comparison of two snapshots using other tools that I don't mention here. But it really does. Again, as opposed to everyone have to manage this themselves, you now have a way of sort of just keeping sort of a long, full history of how things are performing. And you can see big trend, like let's say they do a system update and everything goes down by 10%. You don't have to wait for anecdotal reports. You can see that immediately.
So everything has to be.
Yes. That's right. Yeah. So it's opt-in. It doesn't magically get it from everybody, but it is. The worry originally was it would be too heavyweight performance-wise, but it's honestly not even noticeable from the impacts on the user. Now Flux, so this is where as people have just done work at more extreme scales, we've broken things. And one of the things we've broken is our job scheduler. So we used to just throw jobs at Slurm and it would sort out, but it turns out if you throw 10,000 jobs at Slurm, it gets unhappy. So they recognized this years ago and started writing a much more sophisticated hierarchical scheduler that understands much more complex resource management than the sort of traditional schedulers have. And so the nice thing about this is that it doesn't have to be adopted by this. I mean, it will be adopted by our big supercomputer systems, but a user could run this within a Slurm environment and essentially create a Flux instance that could create more Flux instances and could manage sort of, a three-pronged workflow that, needs to spin off jobs as things finish. And so it really gives people a lot more power to take an allocation and then manage it themselves within there in a much more sophisticated way than just running a couple of jobs one after the other. Now we have other workflow tools coming together. This is basically, you want to do a simulation study. It's similar to what I just sort of outlined in terms of the Flux needing to have a bunch of jobs, but this is a way to express what I want to do and not just have to do it with our usual, my usual simple scripting type of, for each in a C shell script. Instead, you actually can put in some real complexity in a way that's actually readable. And so it's a nice framework for creating and managing simulation studies. This is sort of a simple idea, but one that is really important, which is just, I want to launch quite a lot of jobs. If I was using Python, you don't necessarily want every node to be hammering the libraries or hitting the file system. So instead, you can essentially tell the system to grab the information it needs and then distribute it. And it makes a big difference in performance. And then this is just an advertisement for our big neural network, our scalable neural network software. You're going to meet with Brian Van Essen either today or tomorrow. I don't remember the schedule, but he is the primary author of this, and he will walk you through it. But it's an area where, again, in typical Livermore DOE fashion, we're taking a problem and making it scaling it out to a much bigger size than traditionally people are doing. All right, I'm running low on time. I'm going to be pretty quick on this. So essentially continuing with the theme of the sort of plumbing between codes, we have Conduit, which really simplifies the ability to share data between HPC simulations. Ascent is our in-situ viz tool and our in-situ viz library. Very powerful. It's part of the ECP project as well. So it's really been designed around many use cases. Visit is our long-standing viz tool. ParaView and Visit are kind of the two big heavy hitters in large parallel visualizations. So highly recommend. I've used it most of my career. GLViz is a lightweight OpenGL tool. Looks like it's primarily for finite element visualization. I don't know if it works on other things, but this is one I'm not as familiar with. And then I/O, as anyone knows who's run on leadership class machines, the parallel I/O is always the sort of iceberg. Like, it's hard to get good performance. It's the thing that's broken when you first get on. And so being able to tie into efforts where they really have the sort of latest and greatest interfaces, and they've exercised things like burst buffers. It really, it's just, I can't recommend it strongly enough, as opposed to trying to roll your own. Anytime you can not have to learn how the parallel I/O system is working under the hood, the better off you are. And then we also have, we've had work in compression. This is something, again, as data motion is getting more expensive, as data storage is getting more challenging, wherever you can compress, better. And the thing that's fascinating about this is, in addition to having lossless compression, it also has lossy compression with tolerance. So it's not just compress it, lose a bunch of data, and hope it's good enough. You can really truly say, let's drop the least important bits first, and see, and you can actually watch, as you change those tolerances, how the results look. And at some point they go pretty hinky, but you could lose a lot of data before you really even notice. Okay, so the last little bit I want to talk about is our effort for using the cloud. As I've mentioned, we traditionally have not thought of the cloud as a resource for us for HPC. We have large security-driven mission needs, and that require on-premise resources. But we are seeing that more and more people are using the cloud. We want our software to work on the cloud, even if that is not our primary use case. But we also are suspecting we will start running more and more things in the cloud ourselves. So we are really looking at the cloud as a mechanism for outreach and adoption. And in this vein, we've been collaborating with Amazon, and David Beckinsale organized a tutorial series of 7 of the Radius products just last August. And this is going to be an annual event. We're also hoping to transition this over into sort of a set of tutorials that can be done hands-off on the cloud by others. We'll walk people through how to set that up. But we had a lot of interest. And so we think this is a really promising way for us to do outreach without having to get people accounts or make things very, very heavyweight. Yeah, we had, again, I think we could advertise this more effectively. We had a lot of interest just from the little bit that we did. We also learned that people sign up for things and then don't show up. So provisioning is a challenge because we reserved all the resources for assuming everyone showed up. So we're gonna rethink how we do that in the future. But we were very excited by the interest that we got from that initial foray. Yes.
So
Yes.
I think that's a real positive.
And this is a breakdown of who signed up, and this is something we also found very exciting. The big yellow quarter is Livermore, but 75% was other institutions, including companies, universities. AMD showed up. That was nice. Yeah, so I think there's a lot of interest here, and I think it could grow quite substantially.
Gmail.com.
We have no idea who they are. Yeah,
Yeah.
we hope they weren't anyone sketchy. So yeah, so the way this was set up was really interesting. We essentially did a WebEx with a Slack channel in support, and the Slack mechanism was really important because they are not going to unmute and ask a dumb question, whereas we can sometimes nudge people into asking dumb questions on Slack, and you need that. Like, if you're in a tutorial and you're afraid to ask dumb questions, you're not going to learn anything. And then also, as they do, we asked CS people to put together a tutorial, and of course, instead of just making some slides, they went ahead and developed a whole fancy VS Code instance that ran on Amazon, and people could do things dynamically. And so, yeah, no, the MFEM team really went above and beyond. They had this fantastic, this whole fantastic setup that we are now going to pillage for other tutorials, because I think it's incredibly powerful.
And see David typing away there.
This will be really nice for training also.
It looks fantastic, actually.
Yeah, no, it's, again, I had no idea they were going to do this, but that's the great thing about these people.
See what it does.
Yes.
How to do it.
Yes.
Actually having something real in front of them is really useful.
Yep. And just this sort of environment takes away that sort of canned feel of walking them through like a Jupyter notebook where it's like, oh, now I hit go and then here's the result. I mean, you really can, it feels a little bit more interactive and dynamic. So yeah, so everyone who attended was very happy, and pretty much everyone said that the use of the cloud environment was the best part, that they really liked that everything's happening live. They themselves had an instance they could try things out on and tweak things. And that really does make a tutorial feel more meaningful. Like you've gotten your hands on data. You haven't just watched someone else do it for you.
And I asked whether you know whether people have continued to use the software that you used you demoed on cloud after the tutorial.
Right. Yeah, we have not actually. So the question was whether we can tell if people continue to use the software after the tutorials. Mm-hmm. We probably could look at our download rates and see if they could be on an uptick after the tutorials. I suspect these will be in the noise, just given it was relatively small. But honestly, as time goes on, we might even want to start tracking downloads by institution and see if, a strong showing from a company led to future downloads of other software by that company.
That's exactly what I was thinking about, the long-term impact of what you're doing, because I think that is actually quite an exciting sort of sidearm to this.
Yep. No, it's a great idea. And it's honestly something we're still sort of processing the tutorial itself and figuring out how to keep it going, but I think we should be thinking in those terms. So yeah, so we're definitely going to keep doing this. Again, I cannot give David enough credit. He's organized the whole thing and kept it running smoothly. And he has some thoughts here. He put some thoughts in here on how we can improve. And the fourth one I think is a particularly interesting is if it's a virtual thing, how do you make it feel like an event? And so like old school, we would have had everyone come out here and sit in little, laptops and do things with us. But I think we can try and improve that. All right, so I'm going to wrap up here. I'm going to skip the last couple of slides, but the thing I want to say is one other area where having this open source sort of ecosystem and these tutorials that anyone can sort of come along and try out, I think is really important for outreach in the diversity sense. So I've been giving talks recently through ECP and through the Sustainable Horizons Institute at universities, of minority serving institutions, and places where they don't traditionally churn out a lot of HPC people, because partially they just don't know about it. And so I give talks on DOE and all this sort of science you can do with HPC, and they get very excited. They email me and say, okay, how do I get involved? And I say, well, I don't know, because you can't come and do a summer internship if you don't know anything about HPC. We're not set up for that. But now if I have a whole series of things I can point them to and say, try these tutorials, maybe write a little test code, try and write, I can give them some, problems to work out. They now can show up with some background and have a chance of getting into the next step and really broadening our pipeline, which is something we really care about. All right, so this is just sort of a very wordy rehash of what I was saying, which is we want to start with the usability, and that'll automatically lead to outreach, more engagement, and ultimately, we hope, deeper collaborations. So we're very excited about this new effort. I put the link to the software page. There's a lot of software on there, so use the filters aggressively and don't hesitate to reach out to us if we can help. We will have a new website coming, but it is, of course, not up yet. So that is for the future. But thank you all very much.
Thank you so much for the wonderful talk, Eric.
Thank you.
We're right on time, but let's have some Q&A session.
Sure.
There were some questions in the chat room. For example, by Holly Otten. I don't know if these questions are already answered. Holly, if this question just still stand up, would you mind unmute yourself and ask it? You're still there. Holly, can you hear me?
Oh, I'm sorry, my volume was not great. Can you hear me, Eric?
Yes, I can.
Okay, so I had 3 questions, but you've kind of answered one of them already. So I'll start with that one, which was from what I had heard and seen, I know the attendance on the tutorials was, a fraction, I guess, of what the signups were. But I saw that there was really positive feedback and a lot of engagement from the people who did attend. So I had a question about will that be offered again, maybe different topics or different use cases? And you said an annual event, so that answers that. And then I had 2 other questions that maybe you're kind of linked. One is in an earlier slide you mentioned, or the words that show up are hardening and polishing the software portfolio. So I thought maybe you could elaborate on what those words mean. And then secondary to that is the Radius portfolio, are you going to expand it to include other open source projects, or are all of the categories that you described, kind of all the bases are covered by the projects that are there? And maybe the hardening question answers that in a way. I don't know if that makes sense.
Those are both great questions. So I'm gonna take the second one first. The Radius portfolio is continuing to expand, and in some sense, I think I should be really clear that Radius owns none of this, that this is software that others around the lab have ownership of, and what we are trying to do is provide some additional resources where necessary, just to essentially support making those codes open source and maybe improving the usability or the testing behind them. So the classic example with open source software is you write a piece of code and you use it in your use case and it works great, and so you put it on GitHub and someone else tries it and they build it on using a compiler you haven't tested, or they try it in a slightly different use case and it breaks in a weird way. And so that's what when I say polishing and hardening, I mean just sort of getting some attention on the software from start to end in terms of the user experience. So we would maybe have effort designed to set up a better CI infrastructure to make sure that it's constantly being tested so it doesn't go stale or start breaking on half the use cases. But again, it's not, we can't promise everything will be perfect. It's really more of a, we're going to help move it in that direction. But that is one of the goals of Radius, is just to try and get some attention and from the user side to make sure that an outsider wouldn't come along and just find something that looks really buggy or unusable.
Thank you. That does answer my question.
Great. Thanks, Holly.
All right. So the next question is by Brad. Yeah. He asked, does XBraid play nicely with SUNDIALS?
Wow. I'm hoping someone else on the call is going to answer that one. I have no idea.
So actually, Jeff gave an answer to that. He pointed out that which was good. So the answer was that XBraid is agnostic to what the integrator is. So if you're getting a benefit from SUNDIALS, then you'd still get the benefit from XBraid. So in that sense, they would stack. But so yeah, the short answer is yes, they do play nicely.
Nice, thank you. Jeff's my boss, by the way, so I really love to show up and not know how to answer questions when he's here.
Maybe to add to that, there have been some recent work on providing interface to XBraid from SUNDIALS, so you can use XBraid from once you adopt SUNDIALS. So that's also another way of another way in which they play together well.
Fantastic, thank you, Zanya.
Anyone from audience have a question?
This is Holly again. I'll ask another question. Because Eric said you should be bold enough to ask stupid questions. So I will. So El Capitan's early access systems, we have some that are running. And I guess, or I assume that a lot of these software projects are already testing that out, right? To see how they work with those systems.
Yes. Yes, this is actually one of the arguments I would make for why people should adopt our software, is the fact that we fundamentally, this software is developed because we have mission needs, and those mission needs are long-term. So the code is rigorously tested as on our, at least on the hardware we use for those mission calculations. And so the effort right now for the early access hardware is led out of the El Capitan Center of Excellence. And so we actually, it's a nice partnership with Livermore and AMD and HP and Cray, essentially, to test things out on the early hardware, look for ways in which the runtime software maybe is problematic or there's compiler bugs, and then get those fixed. So it's really about shaking things out before the full system arrives. And that's been a very effective partnership.
The observation, our attempts for the new AMD software stack have been distinctly old.
So the comment was on the new AMD hardware software stack and the performance, and I'm not going to comment on that, but we'll talk more when I'm not being recorded. I'm only going to say good things for anyone listening who is from AMD.
Okay, so there was a
Yes, so yeah, we do have a Slack channel. We've primarily used it for internal developers and for our tutorials, but honestly, we'd be happy to invite others who are interested in Radius to join. So yeah, start by sending me an email, because we don't have our whole mechanism set up as well as we probably should, but at some point we can just put that on the website.
David seems to share the link.
Oh, I love David. He's so good at everything. Delirious from fever and still putting in links.
All right, is there any other question?
I see a hand up.
Please unmute.
Yeah, I have a question.
Go ahead.
So I think it's great. Like, the lab has all these amazing tools. And thank you guys for taking the time to create awareness of them. I just wanted to say that first. And I guess what I would like to ask is, what's the best way to approach the barrier to entry to these codes? So for context, I've seen today a lot of software that I could use on my own projects, like that I haven't played with yet, like Spack or Caliper, Shroud. But for me, the problem is that sometimes for some low-level stuff or some projects with deadlines, I can either spend a day hacking a quick way to do the same thing, or find some sort of workaround that allows me to meet my deadlines, or I can spend multiple days figuring out how to create a file, like a recipe of sorts for Spack, and build my code. Link it to my executable, like reading the documentation for the project, testing, running it. But by doing sometimes, like just trying to create a simple make file, I feel like I will be missing out on skills that I could use in the future. And the obvious answer is to just sit down and invest the time and learn the tools. But this can be difficult sometimes to justify to a project manager that wants you to finish some project, quickly. And it's like, oh yeah, I'm gonna take a whole week to learn to move my make file to Spack. So I guess my question is, what does Radius, do you have any hand-holding programs on demand, in case I missed, for example, the AWS tutorials that could help with the barrier to entry for these codes?
That's a fantastic question. And I think what you're describing is honestly the problem with many open source software projects is you can only go so far in terms of you put up documentation, you put up tutorials, but ultimately it takes a fair amount of time to digest that. And sometimes you're a working example or a person who can kind of sit down with you is going to be by far the most efficient. I can't promise that our software developers can be support. They're very friendly people. So often people from outside have emailed them and asked questions or pointed things out they didn't understand, and they've been very responsive. But that's not a model that scales for us because ultimately these people are hired to do the mission work and they only have so much time for that. But where the HPCIC really wants to go is exactly what you described, is reducing the barrier to entry. And it's going to take time, but Spack would be a natural starting point for us. And it'll be a mix of, Spack already has fantastic documentation and tutorials, but again, it's a lot to digest. So we would pull out sort of use cases or walkthroughs, again, maybe using the cloud, maybe just on the web, where sort of the most common use cases we could imagine would be really clearly laid out, and you could just grab those examples and file off the serial numbers and use them for your own workload. And then from there, that starting point, you can maybe add some sophistication or complexity as you needed it, but you don't have to have that big ramp up time when you first get going on something. So that's our goal. We'll see how we do, but that's something I think we really want to focus on, is that exact use case.
And in terms of getting support, I know, for example, NFM has the GitHub repo, and their responsive time is excellent. Every time I've opened a ticket, they're really good about targeting the problem and offering a solution. So do the other codes have something like this? Because since these are very specialized tools, it's not something you can just go on Stack Overflow and ask about. It's you need specialized support for these questions. So is the best way just kind of contact the project leads, or do some projects offer a point of contact for them to kind of send the emails? I guess what's the best way? Let's assume I do sit down and I open the read the docs file and I go through a couple of examples, but I'm still kind of stuck because my workflow or my project requires has some special case or whatever. Is the best way just to email the project leads? I don't think you provided contact information today, for example, but I'm sure I can find that out. I can find that somewhere. Will that be the best approach?
I would say all these open source software projects are hosted on GitHub, and I would say those pages should guide you to how to get support, whether it's here's the best we can offer from a documentation perspective versus send us an email or check out this Slack channel. And it really is varied. Some of these are some of these are not, they don't have enough funding behind them for it to have a full support team. So it's truly kind of, we're putting this out there and hope it's useful. But I will say that all the people I've worked with, they take the time in their evenings and weekends to try and help as much as they can, because they really do care about these projects. But it is a mixed bag. At some point, I would hope that the HPCIC website would be a mechanism to at least get guidance from my level. Just, here's what I know and here's what I see. Here, maybe try this. But yeah, I'd say GitHub right now is your best mechanism.
Eric?
That's Rich.
Yeah, I just posted a link to the main software.llnl.gov page, which has all the projects on the LLNL GitHub organization organized into different categories with links to the projects. So that's probably the best entry point to find stuff rather than trying to search on GitHub.
Oh yeah, so I should have, thank you, Rich. I should have said that. I have the link up here as well.
Yeah, many of these are Radius projects too, so.
Yeah, that takes you to the full open source portfolio, but that page links directly to all the GitHub repos, and that's the best way to go. You're right. Thank you, Rich.
All right, sounds good. I think we have it.
Okay.
Schedule, I guess. Thanks, Victor, Eric, David as well in background. All right, with that, let's
All right, thank you all for your attention. I appreciate it.
Thanks. Catch you guys later.
See you, Fred.